me with Krzysztof Burdzy from Seattle, WinFix.
Well, thank you very much. First of all, let me say that it's a great honor and great pleasure to be invited to this program and to be able to give this talk at the conference in honor of Greg Lawler. So once again, happy birthday, Greg, and I hope it's okay if I don't have a tie today. Okay, so first of all, let me say a few words. Just a second. No, there are some technical difficulties, but okay. It should work. Let's hope it works. Okay, so first of all, co-authors. So this is a project in progress, so I don't have that a preprint yet. It is partly written. And I just want to say a few words about co-authors. So the project has a root in a different project on a different topics. My first paper was with Sarah Billy and Bruce Sagan, two combinatorialists. It was a purely combinatorial paper. Then there was another paper with Billy, Sagan, and Shumik Pal. Shumik Pal is a probabilist. And later I worked with a postdoc, Lerna Pechlivan, and most recently I worked mostly with Shumik Pal. So some combination of these names will form the authors of this forthcoming paper. And before I go any further, let me say a few words about this project and today's talk. So first of all, the project and today's talk are experimental in two ways. So first of all, this project is partly based on experiments, computer experiments. So I will show you some simulations, and actually they provided sort of significant input. And it's also experimental personally. All my life, Freudian slip, all my life I worked on Brownian motion and potential theory, and working on a discrete model is new to me. So I already got some very significant and interesting input from people, related to this project. But if you have any advice on related problems, known theorems, and so on, I would greatly appreciate your advice. Okay. Before I go any further, let me say a word about the structure of this talk. I will start with a one-dimensional case, which to some of you, or perhaps even to all of you, and to me may look a little bit trivial, but I want to to start with this introduction, the one-dimensional introduction, before I go into higher dimensions, where sort of more interesting things happen. Okay, so first of all, random labelings. I will talk about random labelings. They are simply a generalization of random permutations. So random permutations are permutations, and random means uniformly random in this talk. Concerning random labelings, let me start actually with the last line. If there is a graph such that the vertex set is finite, and I will mostly talk about that case when the vertex set is finite, then I take integers from 1 to n, as many as vertices, and assign them randomly to vertices. And randomly here means that I choose a labeling that is uniformly chosen. Now, so why do I need 0 in some cases? Okay, so there's just basically one example that I want to discuss, namely the case of labeling of integers. Okay, an infinite graph. Think about this as a graph. And I want to use only n labels, a finite number of labels. So they will be assigned to some vertices. So what do I do about the rest? I just put 0 there. Okay, so 0 plays no significant role. It's just to fill the gaps. Okay, so what is a peak? A peak is a local maximum. So why do I talk about peaks rather than local maxima? I told you about the first paper that I had with two combinatorialists. It turns out that it's apparently an established terminology in some area of combinatorics. They talk about peaks rather than random maxima, and anybody would guess what the local minimum is? A valley. Yeah, so there are peaks and valleys. Okay. So this is why okay, and I started by saying that I will consider random labelings, meaning that I choose a labeling uniformly, but from now on I will be mostly interested in conditioned distribution. And almost all the time I will condition either on having exactly one peak or exactly two peaks. So basically for the rest of the talk I will be interested in or talking about just two cases.
By maximum, do you mean strictly bigger than?
All these numbers are different.
Well, you only use the one.
So if the local maximum, if there's okay, having exactly one peak means there's one local maximum. Did you? Okay. Okay, so what I want to do is, you see, I mean, the first case that I want to discuss is when I have a labeling of integers, and as I said, labels from 1 to n will be used once only, and then zeros for everything else. I want only one peak. There is no uniform distribution on integers, so I just say that the largest value is at 0. Okay, so think about n as 100, the largest value. So what can we do? What can we do with 99? Right, the highest value is 100. It is at 0. How about 99? There's only one peak. There's only one peak, so 99 has to be adjacent, because if 99 is not adjacent to 100, we will have two peaks, at least two peaks, right? Okay, so but then I have this cluster of 199, right, of two values, and where do I put 98? Well, if I don't want another peak, it has to be adjacent to to this cluster on the left or right, and we keep going. So basically, what I have is a CK are clusters of the top whatever k values, right, and they are growing one by one, and they have to be always connected. Okay, so this is a simple example. Probably this picture is not very helpful, but anyhow, let me show you. I started with 9, then 8 goes to the left, 7 to the left, 6 to the right, 5 to the left, 4 to the right, then 3 to the right, 2 to the left, 1 to the right, and the rest are zeros. Okay, so this picture I think is much more informative. So in this case, I took, 2 million labels, and I put the highest value at 0. And the question is, what happened to the other labels? I mean, the picture is continuous, but it is supposed to represent, the discrete picture, but except that, there are 2 million dots here, right? So you cannot see the individual dots. And if you think about what was happening here at the top, every time I have to, if I start with the highest value and I add another value, so I will go down the list, then I always have a choice of going to the left or to the right. So in probability terms, it would be I always flip a coin and either add, the next point to the cluster to the left or to the right. So this picture is nothing more just than just the strong law of large numbers, some kind of form of strong law of large numbers. Well, not strong. I mean law of large numbers. You get a straight line because you keep adding, points on the left and right. Okay, so let's have a look at a slightly different situation. You see, please know that in this case, okay, in the previous case, there was this interval and there were zeros extending on both sides. And also, the triangle, the base of the triangle was the whole real line. But in this case, all those extra pieces on outside the interval are gone. So this is slightly different situation. Namely, I have a permutation. So it's a finite set of integers, and I put those integers in a random order. I condition on a single peak. So in this case, actually, the fact that the only peak is in the middle of the interval, it's a theorem. It's not an assumption. In the previous case, I said, assume that it's at 0, right? In this case, it's a theorem that this peak happens to be in the middle. Probably not a... well, I guess it's some kind of a theorem that says that all the other, values or other labels will be distributed as in this picture. So my point here is the following, that the first model that I call uniform growth or whatever, and this model, conditioned uniform distribution, they give you the same picture. So you see a tent. There was a tent in the first case and the tent in the second case. And please note that when I grow these clusters in this case, I cannot grow them in the same way as in the previous case, because if I start with any value, or if I start by placing the largest label at some place, then I cannot simply assign labels randomly, because at a certain point I may go outside the interval. So but it cannot be done in that simple way. And anyhow, I mean, by definition, this is just a conditioned uniform labeling. Okay, how about two peaks? So now let's talk about a permutation. A permutation conditioned on having exactly two peaks. Well, you have to believe me, it's a theorem. And actually, I'm not sure, at least in some form of this theorem appears in my in one of my papers, but I don't want to attribute this theorem to anyone, because I really don't know. You see that the research on peaks of random permutations started in the 19th century. It's just enormous history, and there were many results. So if you ask me to exactly who proved this, I'm not sure if I can answer this honestly. The point of this picture is that when you see the location of the two peaks, it's clear that the peaks don't like each other and don't like the boundary. By the way, I don't know if this is obvious, but there are 4 intervals here, right? From the left end to the first peak, then to the valley, to the peak, and so on. They are equal. Like, this is an asymptotic theorem. And there's also another way of looking at this, namely, let's change the structure of this graph by adding one edge between the ends. So instead of a line graph, we will have a circular graph. It turns out that the theorem still holds, but on a circular graph, that would mean that the two peaks are at antipodal points, or very close to antipodal points. So if there is no boundary, somehow the peaks don't like each other, and they are as far as possible from each other. Okay. So in some sense, the last picture was the starting point for the new projects, because I thought, okay, I would like to prove something in 2 dimensions, and let's try to generalize the last theorem to 2 dimensions. So here's a conjecture. Let's take a torus. I take a torus because I don't want to talk about boundaries. I mean, you could state a conjecture for a discrete square, but let's talk about the torus. And there are n squared labels here. We label the vertices, then we condition on exactly 2 peaks. And the previous picture suggests that the peaks should be far away. And this sounded to me like a reasonable project. Let's see how it works in 2 dimensions and how this can be handled. Well, at this point, I have absolutely nothing to say about this conjecture. On the top of that, whatever results I have, and I will show you what I have, totally destroyed whatever intuition I had about why this conjecture should be true. So the only reason why I still write this as a conjecture and not a problem is because I am emotionally attached to this conjecture. And, but I have no, at this point, I'm not even heuristic, or hand-waving justification. So, if you wish, you can think about this as an open problem.
Maybe I'd see the definitions on the previous page.
Previous. This?
Yeah. I mean, you can have 2 peaks without looking like this.
Again?
You could have a small peak and a big peak, can't you? Or
Yes, so it's a theorem that actually they are both comparable at the comparable height.
Oh, theorem in
Yeah, this is an asymptotic
uniform
theorem.
distribution of all these things. Is that right?
Pardon me? Yeah. So basically, I mean, that 1 million is supposed to mean that we are talking about asymptotic result.
On the uniform distribution of all things with.
That's right. And now okay.
That's the part that I missed.
Okay. Yeah.
When you say that's a theorem, is that a hard theorem to prove?
This hard?
No.
I would say this. Given the current technology, no. I mean, because there are, in some sense, this is related to binomial, multinomial, large deviations, and so on. I mean, so there is so much technology at this point that it's not hard. Okay, so now I will tell you what I know, and so this is a whole bunch of results inspired and somehow related. So first of all, I wonder how many of you realize that the first model that I was talking about was really has a name. It's the Eden model, although I doubt very much that anybody uses the name of the Eden model for the one-dimensional case because it's sort of trivial. So here's the non-trivial case of the Eden model. Well, in this case, it's the two-dimensional case. It's a simulation. And in the Eden model, what you do, you start with a cluster. So that, let's just start with a point, and then you attach a point to the cluster, and you choose one of the boundary points uniformly. Okay, and you keep growing. So in this simulation is actually, so typically I think the model would be on ZD. In this simulation, it's on a torus. Okay, so it was a bounded area. And let me also tell you how to interpret this picture, because there's only one peak actually in this picture. So what I did, just for my own, benefit, is I found it easier to look and interpret the result by putting together 4 copies of the same realization. So I wonder if you see that the 4 blue parts are identical. That's not random. They are actually identical because this is one realization, one omega, right, if you wish, and just 4 copies of the torus. So actually, there's just one peak.
Sorry to interrupt and to go back to the earlier. So, is it?
One can probably prove that in high enough dimension, maybe already 3, the similar thing would not be true, right? Or
the 2 peaks will be close?
yeah.
I have no. I don't have a clue how to do that.
Okay, so
I don't know. Maybe, but at least I don't know. Okay, I think that the color coding is pretty obvious, right? These are level sets, right? The very dark color is the highest value of the. Well, in this case, there is no labeling, but labeling it can be created simply. This is the age of the particle, right? So the first particles, and then we go down to red and so on, and these are clusters, right? Okay, so I contacted some people about the Eden model, and finally they told me talk to Michael Damron, so I did. And we exchanged a few email messages, and I did not understand what he was. It took me several email messages before I understood what he was telling me. His messages were perfectly clear, but my mind was simply closed. I just couldn't read plain English. What he was telling me was that Eden clusters are smooth. My mind was closed because I was looking at my simulations, and obviously the Eden clusters are not smooth. They are fractal. They have some n to power alpha dimension, some alpha dimension. So no, they are as smooth as a circle. Look, my only explanation, because I still believe in my own simulations, is that simply my simulations are not large enough. You see, here there's this fractal froth that has, I don't know, the width of maybe 50, and the whole thing, the whole box is like, I don't know, forget, 100 by 100 or 200 by 200. So it's really small. So basically on this scale, everything is comparable. But if you go to, box of the size 10 to 1 billion, then if you still have this fractal froth of width 50, then yes, it is smooth in that sense. Right? So I don't think that, if I understand correctly from Michael's messages, this result is not proved or published, but he gave me a very convincing heuristic argument based on some also theorems that are already published. So I believe that this is true, what he said, that the boundary is actually smooth in the sense of this dimension, right? I mean, it is k to 1/2 if you have k particles. So this is what you would have in a circle or an ellipse or a square. Okay. So now let's go back to the one-dimensional case. Do you remember that those two pictures that I showed you? There was one tent, and on the next slide there was another tent like this. And I said that in one dimension the two models give you absolutely, the same asymptotic shape. And I guess just by looking at this you will be convinced that it's not the case in two dimensions. So on the left you have the Eden model. On the right hand side what you have is a simulation of the random labeling conditioned on a single peak. And again, there is just a single peak here. That there are 4 copies and so on. So I will show you 2 theorems inspired by the simulations. So actually, let me say first a word about the second theorem. The second theorem, in some sense, is an attempt to prove that the right picture is as far away as possible from the first picture. You see, the clusters in the Eden model has the smallest possible boundary. If you have, n squared particles in a cluster, you cannot have less than n particles on the boundary. And my claim is that in the second picture it's the other extreme. If you have n squared particles in the cluster, then the boundary is basically of size n squared. So we go basically from the smallest possible dimension of the boundary to the largest possible dimension of the boundary. But before I go to that, my first result will be inspired by, I looked at this simulation and that this wasn't the only realization. Actually, I didn't have that many pictures because this was like on the order of magnitude of 1 billion steps. Yeah?
Are you going to tell us how you made this simulation?
I forgot. Yeah. So what I did is I started with the Eden model as some kind of metropolis. Okay, so I started with the Eden model as the initial configuration, 1 peak. Then what I did is I randomly chose 2 vertices, and I switched the values if that operation did not create another peak. And as I say, this is on the order of 1 billion steps. And it looks like it's, at this point, it's stable.
You don't have an argument saying that this will be close to a random sample, or?
Yes, actually. So I wasn't sure about this, but then I thought, I gave this talk, and, what's his first name? Schleifer? I forgot his name, sorry about that. He explained to me that actually that actually my simulation is okay. I simulated what I hoped to simulate.
Can you say again something about the colors in the right picture?
Yeah. So the colors. So on the right, they simply encode the value of the label, because if there are n squared labels used, then we go from n squared, and the n squared has the darkest color. N squared minus 1 slightly, and so on. So the blue, paths that you see, there are, how should I call it, the ridges. Basically, these are, lines with I don't know, lines, some kind of lines with high values. Okay, so I looked at this, and I don't know if you see what I see, but I had a feeling that actually those ridges had stretches of basically line segments, vertical or horizontal line segments. Okay. This may be stretching things a little bit, but actually this inspired the theorem that I can prove. So let me show you what I can prove. So I can prove something in a slightly different setting. Okay, so I will talk about a ladder graph. A ladder graph is really a rectangle, so it's not very interesting, but a ladder graph means that we think about a sequence of graphs. So in my pictures, the height is supposed to be fixed, and you should think about width as going to infinity, right? So it's a family of graphs. It would be an asymptotic result. And I will consider a labeling. And here are some things about this labeling. So I will put the peak, okay, so it's a random labeling, right? And there's only one peak, conditions on one peak at 1, 1. So there's a peak here. Now, it's rather simple to see that there's at least one continuous line, and by continuous I mean here in this case it is nearest neighbor line, like a path, nearest neighbor path, non-self-intersecting, that goes from this point to the right edge. That's elementary. I mean, that's. And along that path, the values go down, are monotone. And this is still elementary. Okay. Now, there may be more than one. There may be many paths like this, so I take the longest one. Okay. There may be many longest paths, so choose one of them in some order, lexicographic order or whatever. So it's best to think about the longest line that goes from the peak to the right edge, and the values go down. So it's like a ridge in the previous picture. So here's the theorem. So let me, try to help you to interpret this. So a certain probability is very small, and this is exponentially small. Please ignore that part exponential, because this is cheap. I mean, the fact that this goes exponentially down to 0 is just irrelevant. It's not very interesting. It's basically the probability, meaning that you get it for free from the argument. So it's just that there is a probability depending on n, and it goes down to 0. Now, what is that probability? So to explain that, imagine that if we have longer and longer ladder graphs, that this blue line has meanders that appear at a certain rate. Say once every 1,000 steps or once every 1,000,000 steps. But that rate does not depend on the size of the graph. Okay? So if the meanders happen at a certain rate, then the length of the line will have to be n times a constant, which is strictly greater than 1, perhaps 1.01, right? Assuming that there is such a rate. And I'm saying that in this theorem, no, there isn't such a rate. Because, you see, this is supposed to be the length of this line is about n, well, not n. It cannot be larger than n times 1 plus a correction. Well, so this is not a very small number, but it does go to 0. So basically what it means that if you have longer and longer ladder graph, you will see longer and longer stretches of the blue line being completely flat. I'm not saying where it is in the graph, but it will be completely flat. Okay, so, well, this doesn't prove anything about that picture on the right, but at least, I would say it gives some moral support to my claim that those ridges are contain horizontal and vertical line segments. Okay, so now here's a rigorous formulation of what I told you about the dimensions. So once again, the probability of something goes to 0. So please ignore this exponential, because this is, as I told you, cheap. It comes out of the argument, and it doesn't have very I don't think that this is very significant. But what is the event? So I look at the clusters. So CK is the kth cluster, and consider the event that actually the boundary is smaller than n squared minus f of n. F is small. Well, not very small. This is only 1 over square root of log n. Well, it goes to 0. Not very fast, but it goes to 0. So suppose that the boundary, is not n squared, but slightly smaller, right? And then I want to, and so basically what I'm saying is that the proportion, because the number of clusters is n squared, right? Because I start with the highest value, and I have to fill n squared vertices with labels, right? Assigned. So the total number of clusters is exactly n squared as the number of vertices. So there's only a small proportion, Fn of n squared, of clusters that have a smaller boundary. So in some sense, most of the clusters have the boundary of dimension 2. Well, anyhow, if I could say 2 minus epsilon, and then this will go over that epsilon for large n. So these are, two theorems about this feature. Okay. So if you cannot deal with a sort of complicated model, then you try a simpler model, and it is quite often that people go to trees, simple graphs, like trees, because then you can prove more. So, well, that's what we try to do. So before I state any theorems about trees, let me tell you, I have to introduce a piece of notation, nxy. This is very simple. If you have a tree and you have two vertices, x and y, then to calculate, to define this number, think about x as the root, and think about the branching structure. And basically, so these are, this is the number of descendants, assuming that x is the root, y is a descendant of x, and these are the descendants of y. Or you can think about this, the blue part is sort of invisible to x because it is screened by y. And this number includes y. So you have to put y in the count. Well, and it turns out that there's a perfectly explicit formula for the probability that there's only one peak and it is exactly at x. And that's it. That's the formula. So the question at this point is, it's a very simple formula. The question is it usable? Because it's a formula, but can you say anything then about it? And yes, there's something that we can say. So here's the definition of a centroid. So centroid of a graph is such a point that if you remove this point, so not a graph, a tree. If you remove this point from the tree, then there will be subtrees remaining, and they all have the size 1/2 of the tree or less. So well, this point has to be at the center in some sense. And you can have either one or two centroids. If you think about linear graphs, then it's either one centroid or two, depending on the parity. And they have to be adjacent. So on large graphs, they are very close relative to the size of the graph. Every tree has one or two centroids, and well, you could have guessed why I introduced centroids, because the peak has to be at the centroid. So if you have two centroids, they are equally likely to hold that unique peak. Okay, so this theorem was a disappointment for me. You see, I had this plan of proving this grand theorem saying that on every graph whatsoever, if you have the random labeling and if you condition on two peaks, they have to be far away. So it's not only on that torus that I told you about, but on every graph whatsoever. And it turns out that it's not true. Because you can fix a distance 3. By the way, you will see two numbers here, 3 and 8. I didn't try to optimize them. They're just small numbers, okay? Probably that you can prove the same with a smaller number. And what it means is that you can have a big graph, and this graph is big in two senses. First of all, it has large diameter because this linear part has size m. M can be huge. And also those stars on the left, there are two stars, star-like graphs. They're also huge. N is greater than m factorial squared. So this graph is big in both senses. The diameter is large, the number of vertices is large, and still the two peaks are very close, and you can probably guess where they are. Obviously, I put those stars to move the peaks close to each other. And there's 8. So why is it 8, right? Well, the point is that I didn't want to go into a very long and complicated proof, so this is just a cheap estimate, basically, right? Because it looks like a rather simple counterexample, so I didn't want to go into a long proof. Okay, so now I will talk about the Dirichlet tree. The reason is this: what are some basic examples of trees? Well, obviously there's a line segment, but then you have random permutations, the classical case, which is not very interesting at this point. And the next example that would come to my mind, although I'm not a combinatorialist, but from an outsider, would be a tree, because it's a sort of nice graph, and in some sense it goes in the opposite. This is the example where we have the opposite to the line segment. There is lots of branching, and then the huge boundary, and so on. So it looks like a natural example to look at from my point of view. So the question is, what can we say about this graph? So before stating any theorems, let me tell you that both Szumik and I were in some sense obsessed with this example, and we wrote long arguments, and both arguments to this day have gaps, and this proved much harder than I would have thought, and I will perhaps try to explain why it's hard. So the theorems that I'm going to state are only 50% true, but I'm not sure which 50% is right. So. By the way, I hope that the definition is clear, right? Because deregular or those trees can be drawn in such a way that the root actually does not have as many edges, right? The degree of the root is sometimes smaller, right? Because this is like a branching structure. No, so here you have only two kinds of vertices, leaves with 1 degree 1, and all other vertices have degree d, and the depth of the tree, looking from the root is constant. Okay. So first, I told you that something about the distance between the peaks. So in this case, the distance. By the way, I don't believe that this is optimal in any way. This is what we could prove. What this says is that the distance is close to k. K is basically the depth of the tree, and the intuitive interpretation is that the highest peak should be at the root or very close to the root, and the second highest peak should be very close to the boundary. And that's how you should interpret this at the intuitive level. And as I say, I'm sure that this is not the optimal estimate. It's just what we have at this point. Okay. So it looks like we can prove that if you want to maximize this function, p of x equal to x, y equal to y is a function of two variables, two vertices, and we may want to maximize it. So I believe that we can prove that it's maximal when x is at the root. So this has to be the highest peak. Please note that d is greater or equal to 11. Well, that's because how the argument works. I have no reason to think that this is actually optimal. I believe that this would hold for all d's, but that's what we have. But here comes the sort of the interesting part, and in some sense this explains why it's so hard to treat this. You see, it appears that once we fix that highest peak in the middle at the root, then the second peak can be anywhere. So you have to look at the order of quantifiers here. What it means is I fix at C some kind of a constant, and so two things are fixed, the degree and that constant, and then I grow the tree. It becomes larger and larger. Okay, and on those trees, all these probabilities are comparable, which basically mean that the distribution of the second peak is uniform. Does that make sense? It's basically uniform. Of course, if you believe this, then it's also easy to see why the second peak should be close to the boundary, because we are talking about the tree, and it's like most vertices are close to the boundary. But this is, I guess a stronger statement. It tells you that basically it's a uniform distribution, up to a constant, obviously. Okay, so I am a continuous probability person and analyst by, well, I hope to be an analyst. So I wanted to do something that is continuous and not discrete. So let me show you. Let me show you what one can do on the continuous side here. So first of all, there's this notion of a subdivision graph. So you take a graph and you subdivide it. But it's not an arbitrary. All the edges in the top graph have length. So actually, I have to tell you an amusing story about this. At least it's amusing to me. I went to a conference recently. It was like on the analytics side, and for the first 2 days, I've heard a lot of talks when people were talking about quantum graphs. And I felt really stupid, like the most uneducated person, obviously, the whole conference. And after 2 days, I went to the web and finally checked, the definition of a quantum graph. And it turns out that this is absolutely trivial definition, because it means that you take a graph and every edge becomes, a line segment, in the topological and metric sense. And instead of talking about what metric graphs or real trees or whatever, you can talk about quantum graphs. So from now on, if anybody asks me what I work on, I will say that I'm a quantum graph theorist. Sometimes you fly with somebody and the person sitting next to you, on a plane asks, and mathematician, quantum graph theorist, Okay, so what I do is basically I think now about taking a quantum graph, and I put the subdivision graph. It basically means that you put a lot of vertices, but the number of vertices will be proportional to the length of the edge, and they will be equally spaced. And now the question is, what do you get in the limit, right? So you have a sequence of graphs like this, and say you have random labelings, you condition them, say, on t peaks, or 1 peak, or 3 peaks, and what do you get? Well, you get something like floodings. So what is a flooding? You remember the clusters, right? If we have, so in this case it will be 2 peaks. If there are 2 peaks, you will have 2 clusters that will be growing, and then the 2 clusters have to be connected, right? Because we can have only 2 peaks. So if you pass to the limit, what you will get is something growing continuously. I call it a flooding because it helps my intuition. I think about this as a system of pipes of, say, unit cross section, and we pump water at the sources. There will be peaks, and somehow the water fills the pipes, right? Okay, so that's so there will be some assumptions here. The cross section is 1. The total rate at which water is pumped is 1. So the total amount of time that it takes to fill all pipes is simply the length of all pipes, because the rate is 1. And I will also assume this can be a part of you can phrase it in different ways, either as a definition or a theorem, but basically let me make it a definition that the rate at which the ends of the arms of floodings move is constant between special events. Special events would be, for example, when two arms meet, and obviously they cannot continue anymore, or if an arm hits a leaf, right? But between that, they all move linearly at a constant rate. So on that interval, you have a constant rate. Okay, so this is a quantity, and so first of all, what are those TKs? TKs are times when something happens. For example, when 2 arms meet or something. Otherwise, you should just pay attention to this part. These are rates. Rates meaning that speed at which the front of the arm moves, and obviously this is some kind of entropy. And the theorem says that when we are thinking about those subdivision graphs, then asymptotically, if you look at the clusters, right, growing in those random labelings conditioned on a fixed number of peaks, then in the limit what you will get is floodings, but those floodings have to maximize this function beta. Okay, so when I showed this to Shumik, my co-author, he doesn't have any respect for me. He said, "Oh, it's trivial. This is Sudakov's theorem," but he's wrong. So first of all, this is not Sudakov's theorem. If you want to actually give a name to this from large deviations, it would be, I think, Mogulski's theorem. But I think that he's completely missing the point, because I'm not trying to redo the large deviation theory. This is just the question what we get on a graph, because those theorems apply to the classical multinomial distribution case. And I think that there are some features here on the graph that are new. So there is a special case where we have some kind of formula. Okay, so this is actually not a good picture because in this picture there are two sources, but this theorem is for one source. Do you remember that absolutely explicit formula for the graph and the peak at a point? So this is the continuous version. So I mean that's, you just have to pass through the limit and you will get this. I just wanted to point out that. So now let me tell you a number of things about the floodings. Okay, so the floodings that are optimal, they have to maximize that beta, that entropy. But what does it mean really? Okay, so they maximize. So first of all, the number of arms is non-decreasing. Right, the flooding will start with some points, at a few points, and then at the very end it will stop when all pipes are filled with water. So the number of arms will be non-decreasing. Please note that they can decrease for several reasons. For example, they can meet, right, and then you lose some arms, or you hit the boundary, so the leaf. So that's impossible. There are no dormant arms, so when time goes on, they never stop growing. So in particular, what this means is that if one arm of a flooding enters a vertex, that it will start flowing in all possible directions. It cannot start flowing in one direction and then after some time flow. The next, the flooding has exactly m disjoint connected components, and they are all trees. So you will never have loops, although probably it is somehow obvious, but from what I said before, but anyhow, there are no loops, so you will have trees forever until the last moment when the whole system is flooded. There are no leaves, again, until the very end. Now, at every time, which is before the terminal time, we have trees, m trees, and those trees are somehow, they grew in such a way that the source. So here's this sort of reversed order, right? Because the centroid idea was that I had a graph, and the question was where's the peak. So here it's the opposite somehow. I start with the source, and the tree is growing in such a way that that point always remains the centroid. But it agrees with the previous ideas, and then in some sense, we know how quickly the arms grow. Now the thing is this: if you have a number of sources, you see the last statement refers to the ultimate shape of the trees, and we have several sources. It's not clear how the whole network will be divided in the end between the trees. But there's one particular case when you have a source, just one source, then obviously the ultimate does that make sense? The ultimate shape will be is known in some sense. So what this means is that the arms always grow proportionally to that part that still has to be filled. Does that make sense, right? I mean, the arm somehow looks ahead and knows how much still water has to be pumped along in that direction, and that's the rate, that's the current rate. Okay, so here's a theorem, and that apparently contradicts what I told you before about trees or deregular trees. On a deregular tree, the flooding, the optimal flooding has sources at the root and the vertex adjacent to it. Of course, there's no direct contradiction because this is a different theorem, but even at the intuitive level, there's no direct contradiction because here we are talking in some sense about subdivision graphs. So, every edge here corresponds to, 1 billion vertices in between. Still, I find it sort of interesting, assuming that this is true, that somehow in this case, that the two peaks are close, the root and next to the root rather than at the sort of root and the maximum possible distance. So, as I said, I mean, the trees gave us a lot of headache, and I will have to double check all the theorems, but at this point, somehow, if this is true, somehow it proves my point that this is a very difficult case if it gives you, one answer in this case, one formalization of that idea, and a different answer in a different formalization of the same idea. Okay, so this is not a particular deep theorem, but I just wanted to go back to that torus case. Okay, so in this case it's a square, and see how my flooding representation fits with what I said before about the torus. So in this case, actually each edge, we are talking now about flooding. So each edge is continuous, right? And you can think about each edge as containing a large number of vertices, right? 1 billion vertices on every edge. And there's this flooding, and the question is how many arms this flooding has. So it turns out that for most times, between 0 and time when you flood the whole system, the number of arms is proportional to the time. So it's t to the 8, between 2 to the 8 and t. This is not a very deep statement. Once you know everything that I told you about how it grows and so on, basically, you cannot have loops. So where do you grow if you cannot you cannot close any loops, right? You're not allowed. The optimal flooding does not close any loops, so it has to branch and it branches, and it gets a lot of arms in this way.
I don't understand. So what is your definition of an arm then?
Arm is the tip. Okay, so let's go back to oh, okay, here there's a flooding. So an arm here is the tip of that set that is growing, because it was in the discrete case it was a cluster, and in the limit it's a continuous set, connected subset of the quantum graph.
Yeah, so I'm confused also because you said all the tips are growing at the same speed.
If they are growing at the same speed?
Didn't you say that?
No, the speed. Okay, so let me show you that, because I have the speed is proportional to the quantity that only God knows, because it's in the future, namely how big is the part of that you still have to fill. So no, that they're not at the same rate. Well, it just happens to be the last slide. Well, I ran out of ideas, so thank you very much for your attention.
More questions?
Now, is there 100% assurance that at least one of the theorems is correct?
99.9.
So the subdivided tree seems to be very different from the original tree, but this guy seems to be very similar, right, to the continuous torus, because you have late points everywhere.
Yes. So that's right. So in one case, you're perfectly right. In one case, it seems to the two representations, right, of this intuitive model give you different results. In this case, there's something that actually supports those simulations, although obviously the model is different, right, because here we have those floodings and subdivision graphs and so on.
On a small graph, can you actually solve that variational problem?
Yes. So on very small trees, maybe, I don't know, 2-3 edges. Actually, I think that up to 5 edges or something that can be done by hand. Beyond that, let me put it this way. I don't have a method. Okay, on very small graphs, you just basically use common sense, and what you know about, how these pieces of a flooding grow and so on, and you can do it by hand. And I did it for some examples, just to see. So, for example, if you have a star graph with only 3 edges, different length, then I can tell you exactly where the source has to be. So just one peak, and it depends. It's sort of actually an interesting formula, because it has something to do with the sum of these edges being longer than the other edge, and so on. So, well, it's not very deep, but it's sort of nice. Once you go to 4 or 5, it becomes sort of ugly, and beyond that, I don't have a method.
You do this in high-dimensional torus. So do you expect these clusters CT to look roughly like lattice animals. So they would be four-dimensional, for example, in the sense.
Okay, so let me make this remark. When I proved the theorem about the dimensions, right, that was only in 2 dimensions, and I actually just because of the simulations, I just limited myself. My rough guess at this point is that a similar theorem might be actually true in higher dimensions. So then you automatically get this, dimension result. So I don't know how that would fit with animals. Do they have the right dimension?
So they look roughly like a random tree embedded in random tree, like branching random or embedded in.
Yeah, but the thing is that DLA also looks like a branching tree. So, and at least I think that the beliefs about the dimension are, for example, different.
Questions?
Did you try to do the sort of back of the envelope calculation of saying, enumerating the number of single things? So you'll get that it will grow, that there will be some exponential growth with some sort of rate.
Of what?
I mean, just the number of single peak guys with n.
Oh, okay. So you take a random labeling and you do not condition on the number of peaks.
No, you condition on one peak, right? So
Oh, you condition on one peak, okay.
One usual.
Uh-huh.
So, I mean,
But then the growth of what?
but the growth of the number of
super exponential.
well, but I mean, these things you sort of can enumerate. I mean, I was just wondering whether it was sort of some concrete. Because then you can enumerate the number of pairs by subdividing and comparing it with the number of stuff.
Okay. So to be honest, I don't quite understand the question. But if let me say something that perhaps is related. There were 2 theorems that I gave at the very beginning about torus and about those straight lines, right? And the other about the dimensions. So yes, it is by combinatorial enumeration. Basically, you try to enumerate all possible random labelings, and then random labelings with a certain property, and
So
yes.
I mean, there's sort of trivial bounds that you get by isoparametric things. The boundary of this thing with n guys will have at least that many guys, and therefore you have at least that many possibilities when you grow an even model. That's not.
For the Eden model? Are you talking about now Eden model or my model?
Well,
For the Eden model, yes. For the Eden model, that's the argument, that the rate of growth and so on. But then it refers to a theorem that is, I think, non-trivial because it has something with the to do with the first passage percolation and the rate of growth. So assuming that theorem, then that there is basically a rather very simple argument, showing that, for example, the size of the boundary.
what you're saying, that sort of simple enumeration things will not sort of lead to a guess to what happens in.
Well, they give you something.
And sort of in the limit when you get it through.
Okay, simple enumeration gives something. I don't know how optimal this is because I did things by hand, and I don't know how optimal they are. So I got some bound.
So let's thank Krzysztof again.